So, let us get ahead with one more example of the trapezoidal rule. So, suppose you have a function which you have to numerically integrate f of x equal to 0.2 plus 25 x minus 200 x square plus a 675 x cube minus a 900 x to the power 4 plus a 400 x to the power 5. It is a polynomial that you have to numerically integrate from a lower limit a equal to 0 to an upper limit b equal to 0.8 with say just one interval. Which means this large polynomial, which is a fifth degree polynomial, has to be replaced by a straight line. Okay. And that is, of course, we know that it is a bad approximation, but still we can integrate it and get a result. So, what is f of 0? It is equal to 0.2 and f of 0.8 is equal to 0.232. So, the integral becomes 0.8, which is b minus a, which is called the h, and the average value at the two extremities, which is 0.232 divided by 2, and this comes out about 0.1728 if you do it carefully, and the exact value is far away. The exact value of this integral is 1.6405. Okay. So, you see that if this fifth degree polynomial is replaced by a straight line and you go ahead with doing the integral using the trapezoidal rule with just one interval, that is, you take the point at the beginning at a equal at a and connect it to the point b, which is 0.8 here by a straight line, this is what you get. All right. So, the error is very visible and extremely large. So, the error is 1.6405 minus 0.1728. So, it is 1.4677. So, a more relevant quantity is that the percentage relative percentage error, this is equal to 1.4677 divided by 1.6405 into 100%, and this is like almost 90%, 89.5%. So, that is the error if you do it. Okay. This is just to show you that trapezoidal rule is has to be carried over to multiple integrals and n equal to 4 and n equal to 6 and so on. We have done a problem earlier where we have compared the results between n equal to 2 and n equal to 4, and that showed that there is a significant improvement. So, the message is that if trapezoidal rule has to be implemented, you better take the number of intervals to be large. Okay. Otherwise, it is going to end up in this kind of an error, large error. If you want to actually calculate the error, let us do it here, that we know that the error is proportional to the f double prime x, which is the double derivative of f. So, this is equal to 400 minus 400 plus a 4050 x minus a 10,800 x square plus a 8,000 x to the power x cube. And so, we have to, so this x actually lies at a point between a and b, where a equal to 0 here and b equal to 0.8. So, we need to actually find out the average value of the second derivative. So, okay, and this is equal to f double prime x. Just to make it clear that so a less than x less than b. Okay, so this is the x lies between a and b, and this is equal to 0 to 0.8, and then this minus 400 plus 4050 x minus 10,800 x square and plus 8,000 x cube, and this into dx and divided by h, which is b minus a, which is 0.8 minus 0. And if you calculate it, it becomes equal to 60 or rather minus 60. So, this the error is actually this was derived earlier. So, the error is equal to minus 1 over 12 into minus 60 into h cube, which is 0.8 whole cube, and this is about 2.56. And you see that the actual error is 1.4677, and we are getting it from these from the error estimate that we have done earlier, which is proportional to the double derivative. It comes out as 2.56. Of course, they are different, but one important thing is that they are of same order of magnitude. So, so what is the reason for such error? Let us write it here itself. Reasons for these discrepancy. One is that we have taken a finite step size, which is as large as 0.8 here, and the other error come from the average value of f double prime x. Okay. So, here if you look at it, we have calculated the average value by integrating the f double prime expression over the full interval and then divided it by the interval. So, that is the average value of f double prime, and this thing is certainly incorrect because of the reason that you see that there are functions which are like x square and x cube. So, for some values of x, say greater than or between 0 and 1, which is the region of integration here, you see x cube is much smaller than x. So, we haven't attached the right weight of this term as compared to the first term that is linear in x. So, this cubic term in x of course, is much smaller for the region that is under consideration, and hence we are getting this discrepancy in the estimation of error. Okay. So, with this we are pretty comfortable with using the trapezoidal rule, which is simply the using the polynomial, the first degree polynomial, and then the entire region of integration is actually converted into a trapezoid, and one calculates the area of the trapezoid by taking the width and the average value of the height. Now, this, as we have seen earlier, that this crude method of calculating the integral of a function can still be improved if we take several segments over which this trapezoidal rule or the trapezoidal formula is applied, and in which case the error actually goes down. So, if you use a number of a large number of segments over which this trapezoidal formula would be applied, then one can expect to get a much better result, which is very close to the actual result. Let us see one more and probably the most popularly used or most widely used formula or rather the formalism of doing integration. It is called as the Simpson's 1/3 rule. And it is nothing but it just uses 2 points rather 3 points instead of 2 points as there in the trapezoidal rule. So, it uses 3 sort of a second degree polynomial in order to do the integral. So, f of x is approximated by a second order polynomial. P2x which of course passes through 3 sampling points. Now, this which 3 is the question. So, let us show this graphically. So, suppose you have okay. So, you have this as the function f of x versus x. So, this is your the initial point A and this is your final point B. So, it uses 3 points, the 2 of them are A and B and the other one is actually an arithmetic mean of these 2, which means the midpoint of these A and B, which is simply let us call it as x 1, which is equal to A plus B by 2. Okay. So, what it does is that it takes this trapezium and it takes this trapezium and calculate the area of each one of them. Okay. So, this entire region is now replaced by this the sum of these two trapezoids or trapeziums and then one calculates this. So, this is a value f of A and this is a value f of B and this is a value which is f of x 1, okay, where x 1 equal to A plus B by 2. So, the 3 sampling points are A, B and x 1 which is equal to A plus B by 2, okay. And it uses a second order polynomial by these 3 sampling points which is P 2. So, just for the benefit of the readers, let me write down the second order polynomial or rather nth order polynomial. So, the nth order polynomial looks like it is a y 0 plus a p delta y 0 plus a p into p minus 1 divided by 2 a delta square y 0 and so on. Okay. So, which is we can write it as a T 0 plus a T 1 plus a T 2 and so on, and then all the way up to say T n. So, that is the second order polynomial sorry there is the nth order polynomial and we are only going to consider the first 3 terms, that is T 0, T 1 and T 2 which are written above. So, we are going to do an integral using these 3 points which is f of A, f of x 1 and f of B. So, a delta y 0 which is a slope will be calculated using 2 of these points and the delta square which is the second derivative will be calculated involving all the 3 points. So, let us see what these the integral becomes. So, retaining the first 3 terms for the Simpson's 1/3 rule, so I, which is the value of the integral, is nothing but p to x dx, and it is between a and b, which is nothing but equal to a to b and a t 0 plus a t 1 plus a t 2 dx. Okay. So, this can be written as a to b t 0 dx plus a to b t 1 dx plus a to b t 2 dx, and let us call them as I 1 plus I 2 plus I 3. So, that is the those are the three integrals, these contributions will have to be combined in order to get the Simpson's 1/3 rule formula. So, I 1 is nothing but y 0 dx between a and b, and similarly I 1 equal to a p delta 0 dx between a and b, and the I 2 becomes equal, sorry, this is I 2 and this is I 3, this I 2 and this is I 3. This is a and b, and p into p minus 1 divided by 2, and so this is a delta 0, we call it a delta 0, sorry, not delta 0, it is delta y 0, pardon me. So, this is delta y 0 and this is delta square y 0 and a dx. Okay. So, this is pretty much that we have to do. Now, remember that dx is equal to h dp, because x equal to x 0 plus ph. So, this comes from x equal to x 0 plus ph, we are going to again show that, and of course, this h is equal to b minus a by 2, because this was b minus a in the trapezoidal rule. Now, it is b minus a by 2 because we are using 2 segments. Now, you see it is important to note that p is equal to, from this formula here, p is equal to x minus x 0 over h. So, x 0 equal to a and x 1 equal to b. Now, h is equal to b minus h is of course b minus a by 2 as it is written there. So, at x equal to a, at x equal to a. Okay. So, see what we are trying to do is that we are trying to change this integral of from x, this now over x, to we will change it to the integral over p. So, we need to know that if x goes from a to b, what would p go from, that is when we replace this dx by dp, then we need to know what the integral, what is the what are the limits of the integral. So, this is equal to a minus x 0 by h. Now, a is equal to x 0. So, this is p is equal to 0. So, at x equal to a, p equal to 0. Okay. So, this is important, and at x equal to b. Okay. So, p is equal to b minus x 0 is of course a. So, this is b minus, now h is equal to b minus a by 2. So, this is equal to 2. So, at x equal to b, p equal to 2. So, when we replace these integrals from dx to h dp, we will have to write from 0 to 2, that is the main idea. So, my I 1 becomes equal to 0 to 2 y 0 h dp, which is equal to 2 h y 0. Okay. Similarly, I 2 would be 0 to t delta y 0 h, there is a p h dp, which is equal to 2 h delta y 0. okay, and I will write it here this thing. So, I 3 it is equal to 0 to 2 delta square y 0, and there is a p into p minus 1 by 2, and then there is a h, and then there is a dp. Okay. If you do this integral, because now it is over p, so it is a p square minus p by 2, and then you have a term which is p cube and all that. So, this becomes equal to and if you when you put 0 to 2, it becomes equal to h by 3 delta square y 0. Okay. So, let me just point out these values of the integrals. See, y 0 is the value of the function at the initial point x 0, which is equal to a. Delta y 0 is the slope calculated at the x 0, and similarly this is the curvature or the double derivative which is evaluated there. So, now how do we calculate all these and get a form for the integral? So, our I becomes equal to h 2 y 0 plus 2 delta y 0 plus a delta square y 0 over 3. All right. So, this is the value of this integral. So, since delta y 0 is nothing but y 1 minus y 0. So, basically this is the value of the function or this is the difference between the values at x equal to x 1 and x equal to x naught. And similarly, your delta square y naught, this is from that the second order formula for the double derivative that we have learned is y 2 involving 3 points to y 1 plus a y 0. Okay. So, y 2 is the value of the function. So, just to remind you that y 1 okay, let us start from y 0 is nothing but f of x 0, this is equal to f at a. What is y 1? It is f at x 1, which is f at a plus b by 2, and what is y 2? It is f at x 2, which is f at b. Okay. So, these are the things that are there. So, your I becomes equal to h over 3 and y 0 plus a 4 y 1 plus a y 2. Okay. So, this is after simplifying and putting in all this. So, all these things are put there, and y 0, y 1 and y 2 have these meaning, and we simply write it as h over 3 f of a plus 4 f x 1 plus f of b. So, this is a nice formula which says that you see you take the value of the function at the left extremity once, take the value of the function at the right extremity once, and at the middle point you weight it by a factor of 4. Okay. And this h over 3 is the, so h is the interval which is here, it is the total interval divided by 2. So, it is b minus a divided by 2. So, this can be also be written as I equal to b minus a f of a plus 4 f x 1 plus a f of b divided by 6. Okay. So, so this is the total width of the segment, and you multiply it by the weighted average of heights f a f x 1 f b. Okay. So, if this word weighted average is not clear, then let me give you an example. Say in the usual semester systems that we have in the various institutions and so on, you have a grading system which is a later grades, which and the later grades actually correspond to points. I mean, these are also there in CBSE and so on. So, one gets a letter grade, and the letter grades has some point in the scale of 0 to 10, and if one gets a B, say B has a weight of 8, which means 8 out of 10, and in a course which has a credit, say it is given by, the credit is given by say 10. So, one would get a whole point for that would be 8 into 10 and so on. So, you have 5 subjects which have all credits, say 10, 8, 6, 4 or 10, 12 and so on, and then one gets a in one course, which means he gets a full 10 on 10 on that course, and if that course has a weight of 4, then it is 10 into 4, it is 40, and then another course which has a credit of 8, one gets a B. So, it is 8 into 8, 64. So, the average will be 40 plus 64 divided by the total number of credits. In this particular case, it will be 4 plus 8, which is 12. We can also give you the moment of inertia example. So, how the moment of inertia is calculated, which is a weighted average. So, the moment of inertia or the position of the moment of inertia is given by it's m I r I. So, let us say it is a vector divided by sum over m I. Okay. So, what it means is that if there is a large mass as compared to all other masses, the moment of inertia or the position of the moment of inertia would be located closer to the bigger mass as compared to the other masses. Okay. And similarly, if there are all masses equally weighted, then the the RCM will lie somewhere in the middle. So, this is that weighted average. We are weighting once the leftmost point, we are weighting once the rightmost point, and we are weighting the middle point, which is the mean or the arithmetic mean of the two end points, we are weighting it 4 times. So, that is the height. So, this heights basically, because this is on the y scale. So, these are the weighted average of the heights. So, this is the formula which is called as the Simpson's 1/3 formula. All right. So, this can be used easily. As I told you that the only difference between the trapezoidal rule and this rule is that it has it includes 3 points for calculating an integral rather than 2 points. And now, of course, you can make a compound this Simpson's 1/3 rule, which means that you can actually split the entire range of integration into several segments, and each one of the segments you can apply this formula. So, let us see the error associated with it. So, once again remind you that this is basically we are talking about the truncation error. So, we have taken 2 terms of the polynomial, or rather the first 3 terms of the polynomial. It is a second degree polynomial. The first 3 terms have been taken, and we are leaving the term from the 4th term onwards. So, this would have or induce error into this Simpson's 1/3 rule formula. So, we can write it as so T for truncation, and let us just write simp for the Simpson. So, it is between this A and B, and in tune with our ongoing notation, let us write T 3, because T 0, T 1 and T 2 have already been accounted for. Okay. And if you write it carefully, then this becomes equal to f triple prime, and let me write some theta, okay, and I will tell you what theta is, and then you have a 0 to 2 p into p minus 1 into p minus 2 h dp, okay, where theta is a variable that lies between a and b. Okay. And this is that third order expression that we have. So, if we have this, because if you remember that we have taken expressions up to the second derivative. So, third derivative is missed out. So, it is f triple prime theta divided by 6, and we have a p to the power 4 by 4 minus p cube plus p square and 0 to 2, because the range of p is from 0 to 2. But you see that if you put 2 here, it becomes 2 to the power 4 is 16 by 4 minus 8 plus 4, which is equal to 0. Okay. So, this is the speciality of this Simpson's 1/3 rule, that the leading order truncation term that contributes 0. So, this is equal to 0. Okay. So, there is no error at this level. So, the error must be at a level which is one more than that. So, the truncation error one has to go beyond. So, usually we have not seen such accidental cancellations, and because of this cancellation, Simpson's 1/3 rule is very accurate, or it is much more accurate than the trapezoidal rule, which has from the second term onwards the error starts coming in. So, this is equal to then a to b and a t to the power 4 dx, and this is nothing but f, writing it slightly cumbersome notation, but it means that there are 4 times derivatives being taken. So, if you have n of them, so you can write it, I mean you can use an alternate notation for f this theta as f 3 theta and so on. So, f 4 theta can be written as f 4 theta. I mean, so anyway, we will go ahead with this notation at this moment. And so, this is equal to this, and then there is a 4 factorial, 4 factorial. So, this 6 is actually coming from the 3 factorial. So, 4 factorial is nothing but okay, we will write it, and the next step we can write it there. So, it is a 0 to 2, and it is a p into p minus 1 into p minus 2 p minus 3 h dp, and this one can be written as h f this fourth derivative divided by 24, and this is like p to the power 5 by 5 minus 6 p to the power 4 by 4 plus 11 p cube by 3 minus 6 p square by 2. This and then from 0 to 2, this gives a finite number which is equal to a minus h f this by theta divided by 90. Okay, so, this is a number which is or this is an error which comes as the fourth derivative and divided by or rather multiplied by h over 90. Since dx is equal to h dp, dx by dp is equal to h. So, that gives that f 4 theta is order of h 4. So, E simp, and let us just write that the truncated one, but the magnitude of that is h 5 by 4 and theta divided by 90. Okay. So, it is so because of this h to the power 5, the error is going to be less, or it is going to be a small error there. Let us see how small and how we can use this error estimation formula to calculate the error. So, let us take an example. I equal to minus 1 to plus 1 exponential x dx, it is equal to h by 3 f of a plus a f of b plus a 4 f of x 1. Okay. I just change the order. So, h is equal to a minus or b minus a by 2. So, h is equal to b is 1 and this by 2, which is equal to 1 plus 1 by 2 is which is equal to 1. F of x 1 is equal to f of a plus b by 2. So, this is equal to a plus b is equal to 0. So, this is f 0, which is equal to, that is the value of the integrand, which is 1. Okay. So, that is fine. So, this is equal to 1, or we can write it as e to the power 0 if you like. So, the integral is equal to e to the power minus 1 plus 4 e to the power 0 plus e to the power 1 divided by 3, which gives a value which is 2.36205. So, this is the value that we get from just 2 segment Simpson's 1/3 rule. So, the exact value of this it is equal to 2.35040. So, this is, if you look at it, this value here is much better than n equal to 4 trapezoidal rule. We will write trapezoidal. Which gave a value which is 2.35040. So, this gives a 2.39917. So, this is the exact value. This is a value from just 2 segment Simpson's 1/3 rule, and this is the value for the 4 n equal to 4 trapezoidal rule. Okay. So, you see that just this 2 segment Simpson's 1/3 rule is itself much better than than that than the n equal to 4 trapezoidal rule. Let us see another example. Okay. So, so it is 0 to, so I equal to 0 to pi over 2 and a root over of sin x and a dx. Okay. So, we will just do 2 segment and then we will see that how it can be increased by a multiple or a composite Simpson's rule. So, then this is equal to pi over 12, okay, because so it is 0 to pi by 2. So, pi by 2 minus 0 divide by 2 is h, and then it is h by 3, just reminding you of the formula that we have used. It is h by 3. So, h is b minus a by 2, which is pi over 4, and then divided by 3 is pi over 12. So, it is pi over 12, and the value at the extreme end taken once, the value at the middle. Now, the middle of pi between 0 and pi by 2 comes the pi by 4. So, we have a f pi by 4 and plus f pi by 2, and this one is equal to pi over 12. It is 0 plus 3.3636 plus 1, and this can be simplified to get, which is 1.142 4 and so on. Okay. You should also check this, because there could be just a slip of calculation from my part, and should see everything thoroughly. So, this is what one gets from this 2 segment Simpson's 1/3 rule. Now, let us see what is a composite Simpson's rule. So, what I mean is that the entire interval between A and B will be divided into n segments. N could be a number of your choice, could be 4, could be 6, and on each one of those segment the 1/3 rule formula would apply. Okay. So, you will have for a small segment, you use a 3-point formula to estimate the value of the integral, then you go to the next segment, use the value of this. So, just to let you give you an idea of this, we have done something like this, where the 1 point here, 1 point here, those are the 2 extreme points. We have taken a point here, which is the mean of these. So, it is a b, a plus b by 2, just a little sloppy drawing from my part. So, let me do it a little better. Okay. But now, you want to actually split them into several such things and use these ones as the A, and this as the final value, the rightmost value, that is B, and then take another value which is in between that is an arithmetic mean of that, then use this formula, go to the next one, again use this as A, this as B, and then use a point in the middle, use this 1/3 formula, and go ahead and sum up all these integrals. Okay. Or so, that is called as a composite Simpson's rule. So, the idea is to divide the entire interval into n segments so that the step size h equal to b minus a by n, where of course, your x I is a plus I h, where I is equal to 0, 1, 2, 3 and so on. Okay. So, we can apply Simpson's 1/3 formula. To each of the segments. Okay. And the segments are x 2I minus 2, x 2I minus 1, and x 2I minus 1, x 2I, and so on. Okay. So, which allows us to write this as h over 3 sum over I equal to 1 to n by 2. So, if you have n divisions, you have n by 2 segments. Okay. So, that is why the sum goes over to 1 to n by 2, and if it is the first one that is taken once 2 I minus 2, that is the leftmost point, and then there is a 4 times the middle point, which is x 2 I minus 1 and plus f x 2 I and so on. So, this is the thing, and this can be written as on a fresh page. So, if you rearrange then your so h over 3 f of a plus 4 times I equal to 1 to n by 2 f of x 2 I minus 1 plus 2 I equal to 1 to n by 2 minus 1 f x, this is x 2 I and then f of p. Okay. So, this is the Simpsons composite 1/3 rule. Okay. So, let me see a quick example of this. So, again if you want h or rather I equal to, so there is an example. So, I equal to 0 to pi by 2 root over sin x dx, which we have done using just a 2 component or 2 segment formula. So, now use n equal to 4 and n equal to 6 segment Simpsons 1/3 rule. So, your n is equal to 4. So, h is equal to b minus a by n. This is equal to pi by 2 divided by 4, which is pi over 8, and so on, and then one can calculate it I equal to pi over 24 and f of 0 plus f of pi by 2. We are simply using this. So, your x k equal to k pi over 8. So, it is 4 pi by 8 plus 4 f 3 pi by 8 plus 2 f pi over 4 and so on, and this is equal to, if you do it, if you put these things carefully and do this, so f 0 is sine root over of sine 0. So, sine 0 is 0 of course, and then if it is pi by 2, sine pi by 2 is 1. So, root over of 1 is 1 and so on. So, I am sort of skipping those intermediate steps. This comes out as 1.17823. So, this is for n equal to 4. If you simply go to the n equal to 6, it becomes equal to, it is like pi over 36, and then I let you write all these terms. For n equal to 6, there will be a large number of terms, and this comes out as 1.18728. Okay. So, this is so basically this is very close to the exact result. And so, Simpson's 1/3 rule simply uses a second order polynomial and builds up a formula from the width of the interval multiplied by the weighted average of the heights. Trapezoidal rule simply uses the average height of the, that is the f a plus f b by 2, that is the average height of the functions, whereas this uses an average weighted average with a point at the middle, and the point at the middle has a weight that is 4 times than the other two extreme points. And here we see that how we can actually use n segment formula to improve the accuracy. So, the whole interval is actually split into n segments, and we have here we of course have even number of segments, because we are taking one point at the middle, and this is the only difference that it has with the 3/8 formula. Besides that, the 3/8 formula may have slightly better accuracy, but nevertheless Simpson's 1/3 rule is more used, and we actually see so this you fill it up, and we actually see that the Simpson's 1/3 rule itself is very accurate and is much better than the trapezoidal rule. And the reason is not too difficult to understand, that you have taken a second order polynomial, which is you have retained terms up to quadratic order, so that the accuracy is improved. Okay. So, this is the main idea behind doing these integrals. We will shortly discuss more methods, but before we wind up for now, let me write down the Simpson's 3/8 rule. That is not going to be used, but it is important for you to know for an academic interest, that there is a Simpson's 3/8 rule which simply uses 4 points. So, now the polynomial uses 4 points instead of 3. Okay. So, this is the thing, and then now the intervals are odd. That is, if you use 2 points in between, then you have actually 3 intervals. So, this is the thing. So, we will write down the formula without proof. It is f a plus 3 f of x 1 plus 3 f of x 2 plus f of b, h equal to b minus a by 3. So, the error is actually slightly better, I mean slightly less. Error is E Simpson's, and I will write in a bracket 3 by 8, and it is really the truncation error. This is equal to minus 3 h over 5 by 80, and now I have again there are 4. So, this is that theta that we were talking about between a and b. So, this if we convert this everything into h and all that, it becomes equal to minus h to the power 5, and so or let us just write b minus a whole to the power 5, and 6480, and this f 4 times derivative this thing. So, if you remember, we will use a, so this number the denominator was 90, or not 90, in fact we have not written it. So, this denominator was in fact, so let me not confuse here. So, if you write this thing, so the denominator is actually 80 over 3, which is you know number which is So, we have gotten a slightly different denominator, let us put it this way, let us not compare and so on. So, this the accuracy is given by this. Anyway, we are not going to discuss this in great details, we will keep using the Simpson's 1/3 rule, which is a more sort of friendly and more accurate or rather reasonably accurate for calculating numerical integration.